If you move a magnet over the surface of a copper material, what do you think will happen? Since copper does not attract magnets like iron, you may think nothing should happen. But surprisingly, when you move the magnet like this, it actually levitates. So why does this happen? When a magnet moves over a conducting surface, the magnetic field at that place keeps changing. According to Faraday's laws of induction, a changing magnetic field produces electric currents in the copper surface. And these currents produced in the copper surface behave like a magnet. So you can think of it this way: the moving magnet creates currents, and those currents act like another magnet. Now we have two magnets, the original one and the induced one. If we know the north and south pole of this induced magnet, we can tell whether these magnets will attract or repel each other. According to Lenz's law, the induced magnet always opposes the change in magnetic field. This means the induced magnet tries either to stop the moving magnet or to push it upward, so the magnetic flux lines do not pass through the copper surface. Because of this, the magnet experiences forces in two directions: horizontal, which is the drag force, and vertical, which is the lift force. Now, if you want to use this idea to make a maglev train, you will not gonna like this drag force because it slows down the train. So what can we do? If you look at the graph of these two forces versus speed of the train, you will notice something interesting. At high speeds, the levitation force becomes large, while the drag force becomes very small. So this type of levitation works best at high speeds. But the great thing about this levitation is that it is very stable. That means if the vertical position of the train gets disturbed, it automatically returns to its original position. Here's how. If levitation force decreases and the train starts falling down, more magnetic field passes through the copper surface as it moves down. That produces strong currents, creating a stronger repelling magnet, and the lift force increases again to push the train back up. In the opposite case, if the levitation force increases and the train starts flying, less magnetic field passes through the copper surface. This produces weak currents, a weak repelling magnet, and gravity pulls the train back down. This method of levitation is called electrodynamic suspension, and it is used in Japan's SC Maglev trains. Now, you may wonder, why can't we make levitation just by using the attraction force between a magnet and an iron-like material? Actually, we can, but this type of levitation is very unstable. Let's see why. If you have ever tried to make a magnet float just below an iron surface, you will notice that it is nearly impossible. You have to place it very precisely so that the force of gravity and the magnetic attraction force become equal. Even a slight disturbance can either make the magnet stick to the iron surface or fall to the ground. So our goal is to keep the magnet stable at one fixed position. To do this, we will use an electromagnet. An electromagnet is a device which can change its attraction force when we change the current flowing through it. The idea is simple. When the magnet starts to fall down, we increase the current, which increases the attraction force and pulls it back up. And if it moves too close and tries to stick to the iron, we decrease the current. Therefore, we can balance the magnet by continuously adjusting the current. This continuous adjustment of current is done using an electronic control circuit. The circuit is connected to a laser sensor that measures the actual distance. We also input the circuit a reference distance, the position we want to maintain. The actual distance and reference distance is given as input to this electronic circuit, which is connected to a battery and our electromagnet. The circuit works like a current controller. Let me show you how. When this error value, which is equal to reference minus actual distance, is positive, meaning actual distance is less than 1 meter, the circuit decreases the amount of current flowing in the electromagnet, which reduces the attraction force and makes the train fall downward and increases the actual distance value to the reference value. Similarly, when the error value is negative, meaning actual distance value is greater than 1 meter, the circuit then increases the current, which increases the attraction force. The train moves upward and the actual distance value again becomes equal to the reference value. In this way, the circuit continuously adjusts the current and keeps the train stable at the fixed reference position. This type of levitation is called electromagnetic suspension and it is used in Transrapid trains of Germany.